Hello everyone, welcome to this channel. In this video we'll be learning gravitational fields. Now the content here is mostly taken from the A-level syllabus, but it's a really broad topic. Anyway, let's start with some definitions first. Now they seem very trivial, but the proper understanding of those really simplifies a ton of problems. So let's start with gravitational fields. Well, let's start with fields in general. Field is anywhere around an object where you can experience a force. Simply stating, where you can feel the influence of an object. It's much like going to a hospital. The moment you step in, you think of all the terrible things that are going to happen, which usually doesn't, but you get the point. So anyway, considering the definition of gravitational field, it is the region around a mass where another mass can experience a force. Okay, looking at the diagram, you can see that I have two masses, a larger mass, capital M, and in the field of the larger mass, we have a smaller mass. All right. So inside the field, inside the region, the small mass M really feels an attraction towards the larger mass, capital M. Now here's the deal. Even the small mass has a field of its own, but we're really considering what field the larger mass, capital M, or the green M, produces. Anything, literally anything that has mass has its own gravitational attraction. Now you can see that I've drawn some lines. These lines, they don't really exist in real life. They're just drawn to simplify problems and also visualize the fields. It gives a much easier image to work with. And these field lines show the direction of a force, of the gravitational force to be exact, in what direction any other object in its field is going to be pulled to. Now, for gravitational fields, as gravity is always attractive, field lines always point toward the object you are considering. So we are considering the larger mass M, and any small mass, it could be any small mass placed anywhere in the field. I'm placing it here, or even here, or even here. They're going to feel or experience an attraction towards the larger mass M. So that the force is always towards the larger mass M. Okay, with that clear, let's move on to our Apple guy. Not Steve Jobs though. So Newton's law of gravitations. Well, before we get in, let's start the third law, like in real details. So the third law states that when two objects interact, they exert a force on each other that is of the same magnitude. That is of the same magnitude, of the same type, and acts on two different bodies. Now this is what it states, but really let's try understanding it properly. So these two masses, M1 and M2, attract each other with the same force, the exact same force F. M1 is attracting M2 with the force F. M2 is also attracting M1 with the force F. Now from the diagram itself, you can see that it's acting on two different bodies. The force exerted by M2 is acting on M1. The force exerted by M1 is acting on M2. All right. So what about the exact same force? Well, I'll get into it in a minute. So let's see what Newton's law of gravitation states. So if two point masses attract each other with a force proportional to the product of their masses and inversely proportional to the square of their separation. So let's write it in simple terms. I guess I'll use the space right here. So that force is directly proportional to the product of their masses. So we have two masses, M1 into M2. This is proportional to the product of their masses. Okay. And it also says it was inversely proportional to their separation. So we can see that the separation is r. So force directly proportional to 1 by r squared, to the square of their separation. Okay, let's combine these two. So we have force directly proportional to m1, m2 over r squared. Okay, so far so good. So if we change it to an equal sign, we need a proportionality constant, F equals k m1 m2 over r squared. Okay, but what is this proportionality constant? Well, that constant is not usually denoted by k, it's denoted by g. So let me erase it soon. It's denoted by g. And g is called the universal gravitational constant. Universal gravitational constant. Okay, what is it? Why is it called universal? Well, anywhere in the universe that you try to measure or figure out the value of g, you will get the exact same value. Now, what is the value? Well, that value is 6.67 into 10 to the power minus 11. Well, this is the number. It has units. I guess from the diagram you could figure it out. So let's writing it all together. F equals negative g m1 m2 m2 over r squared. All right. Okay, I'll get to the negative sign soon. Okay, so this is the formula that works. So by plugging in the values, this looks very cluttered. Anyway, as I was saying, by plugging in the values of m1 and m2, if you, let's say you wanted to find what force m1 exerts on m2, you just plug in the masses of m1 and m2 divided by their separation squared. If you want to find what force m2 exerts on m1, you use the exact same formula. And both of them are going to give you the same answer. Now, at this point, it shouldn't be surprising because that's exactly what Newton's law states. And that force is going to be gravitational force on both. Now, you see, there is a negative sign that I've added out of nowhere. Well, in its actual formula, that negative sign has a lot of significance. So let's actually deal with it a little bit. By standard, gravitational force is attractive, so you always put a negative sign. But there are other examples or other ways to think about it. And I'll try to explain this in much more detail on why the standard was selected and why it makes sense. But it'll be in the next video. Okay, now let's deal with something we call separation. Well, what we're going to deal with is whether we need to consider the radius of the object or not. I mean, clearly these are not point masses because Newton's law of gravitation acts on point masses, right? So, do we need to consider the radius? Well, if the distance between these two, or if r is monumentally large, then you can get away with ignoring the radius of the object and treat it as a point mass. But if it isn't large, then you have to consider the radius of the object. You have to consider the radius of the object as well. And you can't really just use the distances from surface unless they're really far apart. But even if you have to consider the radius for these are not point masses, but because they are perfect spheres, you can in fact think of it as all of its mass being concentrated at the center, and you can simplify problems with it. Now, moving on to a bit more difficult ones, gravitational field strength. So you can see that there is a planet that looks similar to Earth, doesn't have water in it though. Anyway, so let's start with an intuition basically. We know W equals mg. Well, that's pretty much given at this point if you're doing A levels. And weight is a force. Okay, this is a force. Then what is g? Acceleration due to gravity, that's what we normally call it. But let's actually define it more clearly. If we had an object of 1 kilogram, what force would that experience? that force would be equal to G. W equals 1 into G, and that means that force is going to be equal to whatever the value of G is. Okay, but this formula, W equals mg, is highly limited, and you have to stay really, really close to the surface of the Earth. Really close means around like 100 kilometers, but when you're considering astronomical distances, 100 kilometers is really nothing. So what about the actual formula then? Well, let me write it out. Well, in fact, actually, let's discuss the definition of it. Field strength, by its definition, is force per unit mass, which you've seen from W equals mg already. It's force per unit mass. So if you had a 1 kilogram object, what force will that experience? So looking at the diagram, you can really place an object anywhere in the field, and you want to measure what force it experiences. It will be very useful to know what the field strength is at that point. Now, this is a highly exaggerated image, so these distances don't seem to be really large, but in fact it is. So because the distance is really huge, you can't use W equals mg. So yeah, you're doomed right there. So anyway, you can see in this diagram. Okay, so you can see it from the diagram that there is a field around. Infinity is basically region outside the field. Gravitational field really have infinite range, so for simplifying problems, we say that at infinity there is no force. So okay, let's derive the formula right now. Let's make it simple. So Newton's formula for force is GMM. So capital M is the mass that produces the force, or the mass whose field you're considering, and smaller m is the mass that experiences the force. Okay, so minus GMM by r squared. All right. So by the definition, it's force per unit mass. So what I need to do is just to divide force by mass, and it's going to cancel out the units. So minus GM by r squared. This is the gravitational field strength, and it's usually denoted by little g. Okay, so we can see that field strength is dependent on the separation, because we have r squared from the formula. We can see that it's dependent on the separation between the two objects, but it is not dependent on the mass of the object. This is really the reason why all objects get the same acceleration, because per kilogram it experiences the same force. Now we'll move on to some fun stuff. Okay, graphs, basically. It's not really fun for a lot of people, but once you understand how simple it makes physics, and how it can make complicated problems really simple, you'll fall in love with them. So for simplicity's sake, for the field strength graphs, we're only going to consider fields till the surface. We're not going to get deep inside the surface of the Earth. And because inside Earth you have the mass that attracts you towards the center, it decreases. And plus, we like to keep things simple. So in graph, I've already written the formula for gravitational field strength. Okay, so what can I see? Terrible at drawing. That's what I can see. Anyway, so if you can see right here, at the surface you have G as the gravitational field strength. G could be really any value, but I just chose an arbitrary number. So when you move 2 times the distance from the center, the field strength decreases by 1/4. Decreases to 1/4 of the value, sorry. And as you move further, it falls even more and more, but it never quite touches zero. So you could say that gravitational fields have infinite range, which I've mentioned previously as well. Now, what about this orange line here? This is the gravitational field inside the Earth, assuming that Earth is a perfect sphere. Now, there is a very fun derivation of it, but we're not really going to consider that in this video. Apologies for any disappointments. So that's a simple one, gravitational field for one object. But let's try to complicate things a bit, because complicated things are much more fun. Okay, so we have seen the gravitational field of the Earth as a single body, but if we add another mass, and I've added moon, which I did not color. Okay, so let's note a few things down first, okay? So G is the gravitational constant, ME is the mass of the Earth, M sub m is mass of the moon. You could really choose any other letter that you would want, but I really like to use subscripts because that really keeps things much clearer for me. But you're free to use any of these values, as long as you use the formula correctly, as long as your calculations are right. Anyway, D is the distance between the Earth and Moon's centers, and R is the distance between Earth and an object. But we are considering field strength, right? So by the definition of field strength, it's force per unit mass. So whosoever this green guy right here is, although that guy is gigantic, must have 1 kilogram of mass. Must just weigh must have 1 kilogram mass. Sorry, weighing was a very wrong idea. So let's see what the resultant force is, or resultant field strength is. So let's see, if I place an object of 1 kilogram right here, it's going to experience a force towards the Earth, and it's also going to experience a force towards the moon. Moon is trying to attract it towards itself. Earth is trying to attract it towards the Earth. And the distance r is the distance between the object, between Earth's center and that 1 kilogram object. Okay. So from this, you can assume one thing, that if it is closer to the Earth, it's going to get attracted to the Earth. If it's closer to the moon, it's going to get attracted to the moon. Okay, so as standard, I've set up a few things. Towards the Earth, the force is negative. So basically, if any force is towards the Earth, if the force is pointing towards the Earth, then that force is going to have negative value. If it's towards the moon, it's going to have positive value. Well, it's a bit contradictory, but you will understand it soon. So, okay. So these two forces are pointing in two different directions, in exactly opposite directions to be exact. So if you write the field strength, or the resultant field strength, we get this formula: GME over R squared minus GMM into D minus R squared. Note that I have not mentioned a separate distance for the distance between the moon to the object. I've not really labeled this distance as anything separate. What I've used is the idea that the distance from the moon to that object is going to be the distance between Earth and moon minus the distance between that object and the Earth, which you'd really understand from looking at the diagram. Okay, so this is the graph that's going to look like. I hope it is good enough. So towards the Earth, the force is negative, so it starts from negative. At the surface of the Earth, it has the highest negative force. Okay, so as you move closer and closer, actually farther away from the Earth, the attraction towards the Earth decreases and the attraction towards the moon increases. From the graph, you can see that there is a point where the gravitational field strength is 0, because that's the point where a transition happens, where Earth cannot pull that object towards itself anymore, and moon starts dominating. Okay, so at this point there is no gravitational field. I'm sorry, there is the field strength is zero. Field strength is zero, and because of that, the force acting on that object is zero. So any object placed at that point is not going to experience pull from the moon, is not going to experience pull from the earth either. But what if you move beyond that point? Beyond that point, moon starts dominating and the force is clearly pointing away from the earth, and it's pointing towards the moon. And that's why it's positive as the directions. Now, as a fun exercise, by using this formula, try to figure out at what point or how far away from the center of the earth does this 0 point lie. It's a very fun exercise, and I would really suggest that you do it. Now, in a later video, I'll go over potential and potential energy, and I'll also explain the intuition behind why the gravitational potential energy and why this force should be negative. And thank you for watching. Hope to see you next time.